Is there a difference between the brain of a musician and a non-musician? To answer that question, we need to understand how we even perceive music in the first place. When we hear music, the sound travels from our ears into our brain, and that's where we process what we hear. First, air pressure waves, or what we know as sound, are converted by the external and middle ear into fluid waves into the inner ear. This is done through the stops, a tiny bone which pushes into the cloaca, creating varying pressure on the fluid inside. These vibrations in the cloaca cause inner hair cells, sensory receptors, to generate electrical signals to the auditory nerves to transmit to the brain. The signals are transmitted to the thalamus, which then redirects them to the auditory cortex and the temporal lobe. The response thereafter, however, differs depending on each person's past experiences. Music engages many areas of our brain, rather than just one region. Active areas vary within one's individual experience and musical training, since perception depends on grasping the relationship between sounds. Each person processes tone, contour, melody, rhythm, harmony, and timbre in a different way. However, there are common physical responses to the feel of the music, the emotion we gain from different types of music. For example, when you hear this music, you may feel excitement or happiness. Carol L. Krumhansel of Cornell University conducted a study in 1997 in which she recorded heart rate, blood pressure, respiration, and other bodily responses during happy, sad, fearful, or tense music. Each type elicited a different but consistent response. So why do we feel pleasure or displeasure while listening to music? Well, to answer that first question, highly emotional music engages in the reward system in our brains. When pleasurable music is heard, the neurotransmitter dopamine is released into the striatum, which is known to respond to naturally rewarding stimuli like food and sex, which is artificially targeted by drugs like cocaine and amphetamine. Dopamine is released during peak emotion, but also the period known as the anticipation phase. During pleasurable music, the subcortical nuclei is also engaged. This area is responsible for reward, motivation.
EEG scans show our brain's reaction to different types of music. Overall, it seems that our brains feel pleasure during consonant music and displeasure during dissonant music. During consonant chords, the orbital frontal area of the brain is engaged, which is involved in the reward system. During dissonant chords, the right parahippocampal gyrus is involved, which is responsible for dissonance. Although we cannot be sure of all the areas in the brain that are necessary to process music, we can gain some information from patients who have had parts of their brain removed or destroyed. By observing how their perception of music has changed from having certain sections removed, we can determine what areas are necessary or unnecessary. French composer Maurice Ravel suffered from focal cerebral degeneration, in which areas of brain atrophy. Tragically, afterwards he could no longer write music. A patient known only by initials IR suffered bilateral damage to his temporal lobes, including his auditory cortical regions. Afterwards, he could not recognize or make sense of any music. But despite that, he had normal emotional responses when listening to music. This shows that the temporal lobe is needed to comprehend melody, but not to produce an emotional reaction. When the overall auditory cortex, or the primary auditory cortex, is involved in early stages of musical perception, it is retuned by experience, so more cells become maximally responsive to important sounds or tones. Therefore, if you begin listening to music at a young age, you are likely to become more. Now, this may seem like common sense, but the mechanics behind it are much more complex. The more responsive cells then go on to affect further cortical processing in areas such as the secondary auditory cortical fields and etc., areas thought to process more complex operations.
Musicians use the auditory cortex even when they are not listening to music. When they think about a note, they are also engaging the auditory cortex. And this is why some people might think that the brains of musicians are different from the brains of normal people. Another important thing to note is that musicians may only have different reactions when listening to a particular type of sound, usually the sound from the instrument they play. A report in 2001 from the Rotman Research Institute at the University of Toronto shows that brains of professional trumpet players have intense reaction to trumpet sounds, but only that of the trumpet. Now, How does the playing of instruments affect the brain? Well, musicians' brains devote more area toward motor control of the fingers they use to play an instrument. For example, in 1995, Thomas Albert of the University of Konstanz in Germany and his colleagues reported that brain regions that receive sensory inputs from the second to fifth finger of the left hand are larger in violinists, used to make complex movements, while there was no enlargement in the regions controlling other fingers, which do not need to make such movements. Non-musicians do not have these changes at all. In addition, musicians can also develop a greater ability to use both hands, especially for pianists. Current research suggests that this ability, showing increased coordination between the motor cortex of the two hemispheres, may be apparent. So, this is a more complex picture and more detailed picture of the brain. And you can see that the motor cortex is generally found in the middle of the brain toward the anterior side. This seems to be the case since studies show that the anterior corpus callosum is larger in musicians than non-musicians. Other studies suggest that the actual size of the motor cortex is larger. So let's sum up all the areas of the brain that are more active for musicians. When a musician is playing an instrument, the motor cortex and the cerebellum involved in the planning and performance of precise movements are active. Current research also suggests that a region in the frontal lobe enables construction of music and language. Back to this picture. This is where you can find the frontal lobe. In addition, studies show that musicians with long years of training may have improved musical memory, verbal memory, and increased gray matter. And of course, the auditory cortex is also involved. Now, this hyper-development of the brain may seem like a superpower, but in fact it is very real. To get it, all you have to do is pick up an instrument, listen to music more,